Okay, so now I decided to do Norton theorem this week as well. So let's do it quickly. I'll do only 3 examples for this one, and sorry for the shadow. It's quite late at night, so I need to use my light. So yeah, anyway. So we are going to do Norton theorem. I'm going to do 3 examples, showing you the principles of it and how you use it with multiple sources and stuff like that, and some interesting stuff as well with Norton. And I'll try to make this video quick as well, because there isn't much to cover. They are very similar between each other with a few key differences. And as you can see, they are the same steps. Step number 1 is to choose the resistor. Step number 2 is to find Rn and replace V with short and A replace V sources with a short and A current sources with an open. Determine Vn, and Rn becomes a short circuit, and you'll see this in a moment. This is the big change, it's the big difference between those two. And then the last step is to put all of them together. Alright, so let's start with this simple circuit right here. It's got a voltage source of 18, one resistor of 6 ohms, and another resistor of 12 ohms. First, let's select the points. So I'm selecting this one and this point, A and B, to find the unknown RL. Okay, so let's redraw this diagram with the resistors to calculate Rn. So we'll make the voltage source in a short circuit, so this just be a line. There'll be one resistor R1, resistor 2 R2, and here will be A and B. Sorry, A and B, R2 12 ohms, R1 6 ohms. This will be Rn, resistor Norton. And now we can calculate Rn. And as you can see, 6 and 12 are in parallel, which is quite simple. So exactly just like Thevening, Rn is equal with R1 in parallel with R2, which is equal to 6 in parallel with 12, and that one is equal to 4 ohms. So you can already see that Thevening and Norton are already the same basically when it comes to calculating the resistances. But here is the difference when you want to calculate the why did I put Vn? Norton, it's used for current, so it should be In. There you go. But when you want to find out In, well, here is the difference between the two of them. Because let's redraw the diagram again, but this time for the purpose of finding In. So this will be 18 volts, one resistor, another resistor. There you go. And now points A, B, 12 ohms, R2, then 6 ohms, and this will be R1, and here will be the ground. Now you may say, did you dot the diagram wrong because there is a line in here, or do you ignore it? But no, this is actual short. When you are calculating Norton, the current, you are calculating the current going through this wire, and because it's short, this will become a shortcut for a lot of circuits, because being a short, that means the current will flow in this direction like this, and it go in this way, and there will be no current in here. Why? Well, because 12 in parallel with 0, it's equal to 0 ohms. So it's the short, so all the current will go through the short, and it will make it quite simple. That means that the current going through this short, through In, it's simply 18 over 6, and that will be equal with, that's 3, isn't it? Yeah, 3 amps. So that's the answer. So In, it's equal to 3 amps. There you go. Let's box it out. And Rn, it's equal to 4 ohms from the previous one. So let's box this one out. So these are the two key values that we need. Now the difference that between this one and between Norton and Thevening, it's the short circuit, is the circuit that you get from it. So now let's put it together, and when you put it together, you get a current source first off, which will be IN, and then we'll get a resistor, and we'll get another one in parallel. So this will be RL, this will be 4 ohms, and it'll be RN, and this one will be, oops, yeah, this one will be 3 amps, which will be IN. So that's how it looks when you apply Norton. The RL will be in parallel with RN, and it will use the current IN instead of a voltage source. And that's the difference between the two of them. This is what you get at the end of it. However, if you don't want to use the current and you want a series circuit instead of a parallel circuit with two parallel resistors, then you can easily change it by doing so. So you change it to a voltage source, one resistor, and there you go, and then another one here, and we'll get RL, point A and point B. This one will be 4 ohms RTH, and this will be 12 volts VTH, plus minus. And you may wonder, like, how did I get these values? Well, it's actually very simple to translate it, because you simply do the current times the resistance, and that will give you the voltage. So VTH, it's simply equal with IN multiplied by RN, and that will give you 3 times 4, which will be equal with 12 volts. That's how you find VTH for it, by using IN multiplied by RN. And another rule is that RTH, it's equal with RN. The resistances don't change the value, because again, you use the exact same method to calculate the resistance, the RTH and RN, so they will always be the same. The only difference between them, as I said, it's the way you calculate the current and the outcome, giving you a parallel current instead of a series voltage. But this can be easily neglected, because you can change this circuit easily into a Thevenin, series Thevenin. Okay, so this was the first one, and as I said, I'll try to make this video short, because this is more of an extension of Thevenin. Since you won't use this very often, it is easier to use. However, it's not, I don't indicate it, since it relies on currents, and it can get really tricky really easily with currents. But anyway, I'll stop this here, and we'll go to the next example. So yeah. Alright, now let's go through exercise number 2. And in exercise 2, I decided to use a different shape, make it a bit more confusing, by changing the direction, making this way, seeming like all the current will go through here, which mean like, seeming like IN will be equal to 20, even though that is not the case. Anyway, so let's get started. First off, the first step is to decide which one we're going to do, which is the resistor we're going to like find out, which will be that component right there. And then the second step will be to change the diagram to find the total Norton resistance. So there's one resistor here, there's another one here. Very importantly, this one will be an open, there you go, because it's a current source, and current sources are opened. And there will be A, and then there will be B here, and this is supposed to be for RN. There you go, this one will be R1 with 10 ohms, this will be R2 with 8 ohms. And as you can see, it's pretty simple, because this circuit, there's no current through it, so it's just going through here to the top, and it will simply go in a loop. So it's a series connection. So Rn is equal to R1 plus R2, which therefore Rn, it's equal with 18 ohms, and this is the value that is important to us. Rn is equal to 18. All right, now let's go to the next one, and that would be to find out the current. Yeah, okay, so there we can write it two ways actually. We can either rewrite it and just make it like this. There you go. Sorry for the drawings, by the way. There you go. There's the ground. R2, 8 ohms, 10 ohms, R1, and this will be 20 amps. And we need to find out this here, EP. We can either leave it like this and try to work like around it like this, or we can simplify it as well. Because there's a junction here, that means that all three of them are actually in parallel from each other. So 8 is in parallel with the 20 amps and the 20 amps is in parallel with the 10 ohms. And that means that the 8 ohms, the current going through it, it's the exact same current going through AB. So by knowing this, we can redraw it this way, which will make it a lot easier to understand. There you go, there's the current, there is another resistor, and all of them are connected together, and here is the ground. Here's the 8 ohms, here is the 10 ohms, and here's the 20 amps. And we need to find out this wire here, A and B, the current flowing through here. Okay, so the current splits in two directions. It will split direction in there, one direction in there. So the way we do it, it's again through our simple method of, especially this is a current source, so we already know the current. So we can just simply do this and put the 8 at the top, the 10 here, 20 is coming in, so we can calculate. So it'll be like 20 times 8, no, 10 over 18. We use 10 because we want to find out the current inside this resistor, and you multiply the opposite resistor to find it out, and that one will give us 11.1 amps. So therefore IN, it's equal with 11.1 amps, and let's highlight this one as well. And again, it's because the current going through here, it's 11.1 amps. Okay, see, you can see already how easy this is. It's even faster than Theorem, to be honest. And you can make complex circuits simple as well. The problem will be like trying to remember which wire you are trying to measure, which open short circuit you want to measure. Otherwise you might get confused. You might measure like this by mistake, or this one by mistake, you know. It doesn't matter if you measure this one or this one, but the idea is like you still need to be careful about the wire and which wire you measure. And this is going actually pretty fast. I didn't expect to finish so early. So that means that, there you go, IN will be 11.1 amps, and then it will go here to the RN, and the RN will be 18 ohms, and then there you go, there will be the RL with the two dots A and B. There you go. So we again find out the circuit. To be honest, they are fast as well because they are in smaller circuits, and there are only 3 examples as well. And also I did most of the explanation in the other one, the Theorem. And because it gives, I give myself the current, because it's easier to calculate when you have the current. When you have the voltage, it's a bit hard to calculate because you want to find out the current, because the current is the main determinator. Like once you know the current, everything else it's easier to calculate, even if we didn't have the voltage. For example, like in this entire thing we didn't use voltage at all. But anyway, and also we can like find out now what's the total voltage as well, which is pretty interesting. But yeah, so this one was the second exercise, pretty simple as well. just showed how to work with the current source and how you can maneuver the shapes, you know, just change their position and make it easier to understand. And now we'll go to exercise number 3, and exercise number 3 will be the interesting one because Norton theorem can do something that Theorem can't, and you'll see in a second. Okay, so let's keep going. This will be the last exercise for this video, and it's going to be such a short video. It's going to be only like 30 minutes, which is a new record. But anyway, but to be fair, like, this is a short subject as well. Anyway, okay, let's see. So, you may wonder, like, which R are we going to use? There is no RL. Well, this is not really RL, this is supposed to be R2. Well, here is where Norton theorem becomes special and distinct from Thevenin theorem. You can pick any point of a circuit to measure. It's not limited to resistors. So, what I think, I'll pick this point and this point, and I'll call this one A and I'll call this one B. And I think you notice I did multiple things. Like, we got two voltage sources and we got the current source. However, by doing so, by choosing these 2 points, oops, sorry, that was one of my pens. I'm going to calculate only, wait a second, there you go. Hopefully you can see it in the video. I'm going to calculate only what's inside this rectangle, only this side of the circuit. And this is such an important thing to know, and I find it very useful, to be honest. The idea that I can pick up any point I want inside the circuit and I can spread it and separate it, that I can choose a specific section to calculate and leave the rest of it out. Imagine, like, you need to calculate only 2 values, like this from this side there, then it will be so much easier compared to calculating everything, because instead of applying superposition 3 times, you need to apply it only twice. Anyway, so now that you understand that we can pick any point of a circuit and that we don't need to calculate the entire circuit when using Norton, let's get on to calculate this one, which has got a voltage source and a current source inside the circuit. It shouldn't be so hard because the current sources, as I said, it's a way to calculate faster, especially in linear circuits. Okay, so let's start. First, step number 1 was to point out, and we did point out. Now step number 2 is to calculate the resistance. So we'll use R1. There will be a line because there's this voltage source. Here is the short because it's the current source here, and then another resistor here for R2, and that's it. The rest of it is point A and point B. There you go, that's 12 ohms. This one is R2, and then R1, which is 8 ohms. Okay, and you can already see that these two are in parallel from each other because there is the junction, which makes it a parallel, even though it seems in series. Don't forget that there is that invisible resistor line here, even though there is no resistance when the circuit will be measured. So this will be Rn. So Rn is equal with R1 in parallel with R2, and that will be equal with 8 in parallel with 12, and that one will be equal with 4.8 ohms. There you go. So we already found out Rn, and this Rn applies for all of them. Now we just need to, like, calculate In, and we'll have to calculate 2 Ins because there are 2 sources. Good. Now let's go for the first one. We'll start with, like, the voltage source. So let's redraw the diagram. There you go, 14 volts. This one will be R1. This one will be open, of course, because it's a current source. This will be a line here. There will be another resistor here. Close this one up, and the 2 points here, A and B. And let me grab another color and do it. Actually, let's do it with red, so it's distinct from the one above. There you go. And here's the short I, and that we need to calculate. Alright, this one is 12 ohms and this one is 8 ohms, R1 and R2. Alright, now I don't know if you noticed this, but there's a short circuit between those two, because there's a resistance of 0 in here and there's a resistance of 12 here, which will mean this is a short. And what happens if there is a short? Well, as you know, the current will go through here, it go through R1, so it passes through one resistor. There is nothing here, it's an open circuit, so it passes by this one. And because there is no resistance in here, all the current will go through Rn, and it will ignore this point here. It ignored the resistor R2. So there is no current going through R2, which means it will make it very simple, which means that we can determine IN1. Let me put the one in this one as well, because we need to do for both sources, and this is the first source. IN1, it's equal with V over R1, which is equal with 14 over 8, and that's equal to 1.75 amps. So that's the first answer, 1.75 amps. Again, because 12 in parallel with 0 is to give you 0, so all the current goes through here to IN. So we don't need to integrate this, we don't need to calculate the parallel of this resistor. Alright, now let's go to the next source, which will be the current one. So there will be one resistor, it's a short circuit, so there will be nothing else. Then there's this one here, the current source. Then there's another resistor here, the 12 ohms, R2. And again, point A and point B. And let's use the red pen again. And this one will be IN2. And you'll see in a moment why I didn't make the current direction yet. So this will be R1, 8 ohms. This one is 16 amps. And this one is 12 ohms, R2. Alright, now here is the interesting part. So, all three of them in parallel, yes? Well, this will be proven as a problem because 8 in parallel with 12 in parallel with 0, it's still equal to 0. There is still 0 resistance in total. That means it's a short circuit. And as I said, now you can see why it's so easy to calculate when you have a current source, because simply the current will go through here. Yeah, there is nothing here, so no current will go through here, and no current will go through here. All the current will go through I2. So there you go. So you go in this direction through I2. So there you go. The current moves up, it moves that way. It doesn't go through here. It moves back where it came from. It doesn't go through here either. Again, because it's a short circuit. So IN2, it's equal with 16 amps. It's the same current as the source. So that was pretty simple. Okay, now we need to calculate the, yeah, it is 16 amps. Okay, I thought for a second I used another value. Right. Now we just need to put it together, don't we? So we need to determine what IN is equal to, and we need to decide the symbols. And I don't know if you noticed, but they will be negative. They will be, I guess it just to be IN2 minus IN1. Why is that? Well, the current in IN1, it's coming from point A to point B. However, the current in IN2 is going from point B to point A. They are opposite directions, which means that one of them has to be taken away from the other. One of them will put resistance against the other. So then IN total is be equal with 16 minus 1.75, and that will give me 14.25 amps. So IN is 14.25 amps. So let's rewrite them here. So Rn is equal to 4.8 ohms, the first important one, and IN it's equal with 14.25 amps, the other important value. Okay, so far everything is good, and now that's everything really, isn't it? Yeah, but let me show you how it looks like when you connect it, because now the circuit will look like this. Which direction do you think the current will go? Do you think it will go up, or do you think the current will go down? Well, the current will go down. It go this direction, and let me explain you why. You see, the voltage, if I1 was bigger than I2, then the current will go up, because this is the direction of the current in the first um, drawing, in the first diagram. However, this current was proven to give us a positive answer, which means the current is flowing in this direction, as in diagram number 2. If when we did IN2 minus IN1, and if we got minus 14.25 amps, then the direction will be the opposite of this one here. So again, when it's a minus value, the direction is opposite. When it's a positive value for IN, then is the original direction. Okay, it's important for you to know this. It's for everybody to know this, because like I made like many mistakes in any. Sorry, it's late. It's quite late. I bet this is an easy mistake that everybody can make. Anyway, let's see here, and then we do that, and then we put here the resistance Rn, which will be 4.8 ohms, and then we put here the 2 A and B, but don't forget about the rest of the circuit. And now we put the rest of the circuit, which is the resistance R3, which is 18 ohms. This is minus and plus 24 volts, and this one it's R4, and that will be 20 ohms. Again, like I could have chosen these 2 points to calculate it and do all 3 sources. However, I wanted to show it to you that you can choose any points in a circuit and simplify it. So we basically simplified half a circuit into this here with one IN and one RN, and we can make it even simpler as well. We can make it in a voltage source as well if you want. We can simply do this plus minus, and then we do, let me do on the calculator because I didn't have this one prepared. 18.25 times 4.8, so that would be 87.6. So 87.6 V, so that would be VTH. Yep. And then this one will stay the same, so RTH will be 4 oh no, wait, it's not in this direction, it's in this direction, because it becomes a series one. 4.8 RTH, and then it will be like point A. This one will be 18 ohms R3 minus positive, yep, 24 volts. This one will be here, that will be R4, that will be 20 ohms. There you go. And this will be the circuit transformed into Theorem. Instead of having a parallel resistor with a current source, we made it into a series, that's called in a voltage source in series with a resistor. And again, to find out VTH, it's simply 18.25 times 4.8, that give us 87.6 volts, and Rn will always be equal with RTH. And this one was IN multiplied by Rn. There you go. Sorry for the writing. Anyway, so that was the last one. Exercise number 3. So hopefully you understand how to do it. It's very similar to Thevening, except with the exception of a few rules, with the exception that you use current instead of using voltage to calculate it. And even if and it depends, you need to choose like when this method becomes easier than Thevening, and when Thevening it's easier than this method. But again, I recommend to use Norton though when you want to separate circuits, when you want to have to know half of it and still have the other half as the original. But anyway, this was the Norton theorem as well, with 3 examples, and hopefully you find it useful. Because like the way is that's the only reason I do these videos, to like contribute to something, I guess. Contribute to something, I guess. Because like that's the way that I learn as well. Sometimes I just watch YouTube videos. Anyway, so I'll see you guys next week doing delta y transformation, and with this we officially finished the the first what's called, not the first year. I wish so. We finished all the linear circuits analysis methods. So these are all the methods that you can determine the resistances, the currents, and all the methods that you can use to simplify a circuit. So yeah, I'll see you next week. Bye.